Okay, this video is going to be on more examples of refraction. These are the papers. I'm going to take a picture of them and put them up on Schoology to go along with this. They're the same, honestly, as the last examples we did, or I showed in another video. First thing we need, I should say the same type of examples. First thing you need is the index of refraction. Once again, you could look it up online. You could just Google it. Now, they might be off just barely, but for example, if it says quartz, or it says like, what do we got here? Methanol or water, stuff like that, they should be pretty close to the actual. Crown glass is always 1.52, but anyway, if your values are a little off because you have different index of refraction, that's fine. Just when you write the problems, you would see that in there that it's a little bit different. Okay, so here's the examples, okay, from classroom physics. Some of you might be familiar with that. I can't remember if it's that or hyperphysics that people are very familiar with for their labs. And I think you know what I mean. All right, so the first one here, it says light travels through a vacuum, all right, with a speed of this. Normally we round that to 3.00, but that's fine. We'll leave it. Determine the speed of light in the following media. Okay, different substances. So when it comes to that one, that is not Snell's law. That is n equals the speed of light divided by the velocity of light. If you recall this, c is always going to be greater than v. That's the speed of light in a vacuum, the fastest it can go. This is the speed of light, which would be less in a substance. So let's just take crown glass, which is actually 1b. It tells us the value of speed of light in a vacuum. Like I said, a lot of times we just use, or all the time we just use 3.00, but in this case they didn't, so we won't. And we're looking for the velocity. I kind of messed this up, but the n in crown glass is 1.52. So we are solving for the velocity. So v would actually be equal to c divided by n if we do the algebra. 2.998 divided by my index of refraction, and that will give me a velocity that is less, and I wish I had my calculator. There it is. Okay, so the way we type that, hopefully you can see, is 2.998 EE to the 8th divided by 1.52. And we get some nice huge monster number. So really it's 1.97 times 10 to the 8th meters per second. Okay. And you would just do the same thing for all of these. You would just be putting in different n values. All right. Second one. It says, consider the 3 diagrams below. Measure the angle of incidence or refraction for each of these diagrams. We have a problem. And we're not even in Houston. Problem is we don't have a protractor, so guess what? No doing number 2. Problem 3. It says a light ray travels through air, so it gives us 1 for the index of refraction. It approaches a boundary with water, and it gives us the index of refraction of water. It says the angle of incidence is 45 degrees. So if I make a quick drawing, just draw a line, okay? Draw an arrow, okay? Tells you that this is air, 1.00, and this side is 1.33. It also tells us our angle of incidence is 45 degrees. Okay? Now we should know if we go from a low to a high index of refraction, our angle is going to be less down here, so it bends towards the normal. Recall that this is the normal. Okay. It says determine the angle of refraction. So actually what we're looking for is theta 2. So this would be theta 1. Oops, theta 1. You could call it theta I for index, or I'm sorry, for incident angle. You could call it theta 1. I normally call it just theta 1. And I actually know that it's going to bend this way, so I'm going to draw it. If you don't know, don't draw it. Okay, So this sides are my 1s, this sides are my 2s. Snell's law. Okay, if you like to plug in your numbers here, please do, but we are solving for this. So the first thing is to divide by n2, okay, and then we'd be left with sine theta 2, and then we do inverse sine. Okay, put our numbers in, n1, 1.00, that's always nice. Sine of 45, you folks probably know what that is without using a calculator. And n2, index of refraction for the second one. So 1 times sine of theta is just sine of 45 divided by 1.33. You get this number. Then you take inverse sine, you get 32 degrees. Okay, nice. It's very nice. 32, 32.1, that's fine. So why do I say it's nice? Because I know based on just I can't think of the word. Anyway, based on just knowledge of how physics works with the angles, we don't need to know any math. We know low to high bends towards normal. If this was higher than this one, it would bend out this way, away from the normal. First couple down. Let's take a look maybe at one more. Okay. Now, if there's some of these that you want to do, feel free to do them. And then just ask me for the answer. Or see how it says you can actually go online and find the answer? That's probably the better way of doing it. Okay. This is a great one. I don't know how to say this name. Ray Zuvlight, number 5. During a physics lab, Ray Zuvlight observes a laser line passing through the phone call. Passing through an unknown material. So with that said, if it's unknown, that means we're not going to have the index of refraction. That's probably what we're going to have to find. All right? So it goes through an unknown material towards a boundary of, with air with an angle of incidence of 24.5. The light ray emerges into the air with an angle of 33.8. Okay? So, number 5. It seems like we don't know a whole lot, but we do. The way it's worded is also a little bit confusing. Normally, when we have these, we start in air and we move to something else. In this case, it tells you that you're in something else, and then this side is air. Okay? We know the index of refraction of air is approximately 1. Okay? It's actually a little bit higher than that, but it's way out to more decimal places. All right? Now this side, I'll call this N2. N1, we have no idea. Okay? It also tells us that the incident angle is 24.5. So this hits at, I'll try to make this all nice and square, hits at 24.5, theta 1, and then it tells us it goes this way. The angle actually increases. And it tells us theta 2 is 33.8. So I like this, okay? It tests just the common physics knowledge here, right? So what do we know? This is 1. We know that it goes away from the normal, so low angle, bigger angle. That means that this n has to be greater than 1. Now, of course, we know that, okay? In the better way, probably write it has to be greater than n2. Now, come on, we should know that because it can't be less than 1 ever. So we know it has to be greater. But let's just say this was quartz, 1.52. Quartz? Oh, I'm sorry, crown glass, 1.52. Then it would be like, well, this could actually be bigger or smaller. What is it? And we'd be able to use this knowledge of which one's bigger and how does it bend based on that to figure it out. So we're trying to find n1. n1, sine of theta 1, n2, sine of theta 2. Now, a lot of times students do not like to mess around with the thetas. This is your best one. They don't like the inverse sign. This is a good one then, because you're solving for this. n1 after we solve this, basically you have done every type of problem. Oh, I didn't put those angles there. All right, so we don't need to put the 1 in because 1 times the number is the number. So we have sine 33.8. I don't know why I like to do this though. I just like to hit equals. And then divided by, I forgot sine here. Divided by sine 24.5. And we get 1.34. The nice thing about this is, you know the number has to be greater than 1. We never have an n value less than 1. Okay. So if you do that, you probably had switched something over here. You flipped it. Put maybe the angles in the wrong place. All right, so those are 3 quick examples. Like I said, you could do other ones. Go online. It actually looks like it has an audio guide solution. That'd be fun, and it wouldn't even be my voice, so you could listen to somebody else. And then you can also click the show answer, and it will show you. Or just email me. We'll figure it out. All right.